This is part 2 of our lesson on inverses, and we're going to start by reviewing the key points from part 1. So key point number 1 is that inverses have x and y coordinates switched. So a single point AB would switch to BA, and the domain of one would become the range of the inverse. The range of the first would become the domain of the inverse. Key point number 2 is that inverses are reflections across the line y equals x. And we also saw the process to find an inverse. Sometimes we have a step 0, which is to rename the function as y, and then we switch x and y, we solve for y, and then we rename the inverse. If the original was f of x, the inverse is f inverse. If the original was g of x, the inverse is g inverse, etc. Okay, it's time to move on. This is example number 3. Find the inverse of g of x equals x squared plus 1. Okay, I'm going to start actually by looking at the graph of my original function, g of x equals x squared plus 1. So we know that to be a parabola that opens up, and it was shifted up 1, thinking about transformations. So just a quick sketch of that parabola, it would look something like this. And we're going to find the inverse. And we know that inverses are supposed to look like reflections across the line y equals x. So we should be expecting something like, let's see, the point 0, 1 would switch coordinates, and then we would have 1, 0. And then we would have this point here, that point there. We're expecting something kind of like that, more or less. Okay, let's go through the algebraic process. So first I'm going to call g of x just y. So we have y equals x squared plus 1. And then step 1, switch x and y. Now we have x equals y squared plus 1. And then step 2, solve for or isolate y. And again, if you like, just rearrange your equation to put the y terms on the left if you like that better. And let's subtract 1 from both sides, and then let's square root both sides. And remember, when you're square rooting, you do need plus or minus in front of the radical. I'm actually going to pause before I do step 3. So you may remember from the day that we looked at the graphs of basic functions that if you had the basic function y equals square root x, it looks like this. And if you were to shift it to the right one, you would get y equals square root x minus 1, which looks like this. And I believe that is what we're seeing over here on this inverse. This is the part that corresponds to the positive square root. And then we also know from our study of transformations that if you multiply by a negative, you'll have a reflection across the x-axis. So that is the part that looks like this. So that makes sense that this right here, the inverse that we found, is just made up of two different square root graphs, the top one and then its reflection down there. Here's the thing though, if I was to rename the inverse as g inverse of x, this looks like function notation. Just like g of x is function notation, g inverse looks like function notation. However, this graph here, this is not a function. This fails the vertical line test. So really, we're not supposed to use this particular naming notation if it's not a function. So I'm going to skip step 3. In fact, some mathematicians would say, if the inverse is not a function, the inverse does not even exist. They would just say there is no inverse, and they would leave it like that. That's not important to me. I think it's okay personally to say this is the inverse that we see right here. It just happens to not be a function. Okay, let's look at example number 4. Find the inverse of h of x equals x squared plus 1, which is the same function we were looking at in example number 3. However, there's this extra part. X is less than or equal to 0. So we have a domain restriction. We're only looking at part of the parabola, the part where the x values are less than or equal to 0. So that means we actually have just half of the parabola. Let's try that again. Something like that. I get the idea. Okay, so let's go through the process. Rename h of x as y. So we have y equals x squared plus 1. switch x and y, x equals y squared plus 1. Solve for y, so subtract 1 from both sides. And I'm just going to rearrange y squared equals x minus 1. Square root both sides. This is exactly what we did in example 3, but it's going to end a little bit differently. So remember how in the original it said that x was less than or equal to 0? And remember how we've talked about how your domain and range switch for an inverse? So if the original has x less than or equal to 0, then for the inverse we need y to be less than or equal to 0. So we only want the piece of this answer that corresponds to y values that are less than or equal to 0. That means we only want the negative y values. And if you think about the graph that was drawn on the last example, the one where we took the square root graph and reflected it across the x-axis, we got something like this. Doesn't that look like the reflection of our original across the line y equals x? I would say indeed it does. Now, is that orange graph I've just drawn there, is that a function? Does it pass the vertical line test? It does indeed. So can I go ahead and rename it? Yes, I can. I'm going to call it h inverse of x equals negative square root x minus 1. Okay, little extra note for you here. I'll drag it back over a little bit. For a function's inverse to also be a function, the original must pass the horizontal line test. So if you take a look at my original function, of course it passes the vertical line test, that's what makes it a function, but it also passes the horizontal line test, meaning every time you pass a horizontal line through, you only go through one point, never more than one. Well, then when you find the inverse, you're going to take all those horizontal lines and flip them into vertical lines. It will pass the vertical line test, the inverse will, if the original passed the horizontal line test. A function that passes the horizontal line test is known as a one-to-one function. A little bonus information for you there. Okay, here's key point number 3. If f and g are inverses, then f of g of x equals x, and g of f of x equals x. Remember f of g of x, or also written as f of g, g of f of x, g of f. We're talking about function composition, one function inside another. Well, what happens when you have inverses is the inverse operations cancel, a plus 1 and a minus 1, a times 2 and a divided by 2. And because of that canceling, you're expecting only to have x left after you've done composition. So here's example 5. Use composition to verify that y equals 2/3 x plus 1 and y equals 3/2 x minus 3/2 are inverses. You might recognize these functions from example number 1 that we did in the first video, and we know they're inverses. We're just being asked to verify or prove that they're inverses through this process. So here's what it looks like. Suppose I call this one f of x, and suppose I call this one g of x. Okay, so let's find f of g of x. F of g of x means we're going to put the g function on the inside of the f function. So we're going to replace this x in the f function with all of this. It's going in there. So that's going to give us 2/3 times 3/2 x minus 3/2. That was put in place of the x, and then we still have the plus 1. And now we simplify. So distribute. 2/3 times 3/2 is 1, so that gives us 1x. Again, 2/3 times 3/2 is 1, so that gives us minus 1. And then we have the plus 1. And then when you add the plus 1 and the minus 1, they add to 0, so all we have left is x. And then for the second half of the verification, g of f of x, we're putting the f function inside the g function. So not this anymore, the other way around. So at this point, all of this f function is going inside for x in the g function. So that's going to look like 3/2 times 2/3 x plus 1 minus 3/2. And now we simplify. So distribute your 3/2. 3/2 times 2/3 is 1, so we have 1x. 3/2 times 1 is 3/2. And then we still have the minus 3/2 at the end. Combine the like terms, and all we have left is x. So that's our verification that according to this algebraic process, yes, we do have inverses. One more time, let's go through that with example number 6. And it looks like part of it got cut off, so I'm going to have to do a little fiddle. Okay, there we go, back in business. So you might recognize these two functions from one of our previous examples as well. I think it was, I don't know, example 3 or 2 or something. Doesn't really matter. Use composition to verify that these are inverses. Okay, so this time I've called them f and f inverse, so I'm going to show that f of f inverse of x equals x, and then I'm also going to show that f inverse of f of x equals x to verify or prove that we have inverses. So here the f inverse function is on the inside, so we're putting it inside the f function in place of that x. So we have 2 times the cube root of 1/2 x plus 3 cubed minus 6. Now, of course, the cube and the cube root cancel each other out, so that leaves me with 2 times 1/2 x plus 3 minus 6. Distribute the 2, and we have x plus 6 minus 6, and then add the like terms, and all you have left is x. Same idea over here, but this time we are putting the f of x function on the inside. So the outside function is f inverse, so we have the cube root of 1/2, and now for the x we replace it with 2x cubed minus 6, and we still have a plus 3 in there. And let's simplify that. So we have the cube root of, now we can distribute the 1/2. 1/2 times 2 is 1, so that's x cubed. 1/2 times 6 is 3, so that's minus 3 plus 3. Notice we can add the minus 3 and the plus 3 together inside that cube root. And now all we have left is the cube root of x cubed, and the cube root of x cubed, of course, is just x. So again, we have verified inverses using this algebraic process of composition. There are other ways to verify inverses, such as graphing, and also such as just taking one of them, switching x and y, solving for y, and showing that you do get the other. But if it says use composition, that's the process you want to do. And that is the end of video number 2.